So let's look on how nice it is the proof that the eigenvalues of a self-adjoint matrix, let it be a symmetric, let it be Hermitian, namely symmetric over the real and Hermitian over the complex numbers, or let's call it symmetric in a Euclidean space and Hermitian in a unitary space because we're talking with inner product. So how nice it is to see the proof for this, that the eigenvalues of a self-adjoint matrix or transformation are real. Why? Because take an eigenvalue lambda, take an eigenvector non-zero because it's an eigenvector, V of a self-adjoint matrix A, so it satisfies the properties of eigenvalue and eigenvector, AV equals lambda V per definition. So let's take the inner product between AV and V. So instead of AV, I can write lambda V. And I can take bilinearity, homogeneity. Specifically, I can take this lambda out, so I can get lambda V and V. Now, because it's self-adjoint, I can also calculate another thing. AV and V inner product equals V AV and not A adjoint, because the adjoint is self-adjoint. It equals A, so you can write it A. And this equals V lambda V, and in a unitary space, you can take this lambda out, but with its complex conjugate. So it's complex conjugate lambda V and V. Now, those two are equal, right? Those two are equal. So this equals this. So this one. Now, you know that V is not 0 because it's an eigenvector, and by definition, eigenvector is not the zero vector. So you have here in a product between two vectors which are not zero. And if you remember, by the positive definite of norms, the inner product between the same vector is always positive unless the vector is the zero vector. But it's not in this case because it's an eigenvector. So you can divide by inner product of V and V on both sides and get that lambda equals its complex conjugate. But which complex number equals its complex conjugate? Only real numbers. Therefore, the eigenvalue, and this you can do for every eigenvalue of the matrix, this process, so every eigenvalue of a self-adjoint matrix, let it be in Euclidean space, let it be in a unitary space, you get that it's a real number. Very nice proof for the fact that all the eigenvalues of a self-adjoint matrix of transformation, all of the eigenvalues are real numbers. And thank you all. Thank you very much, and that's it.